Hi everybody, I'm going to go for an 11.1 problem. These are all basically the same. So I'll just jump right in here. I think we'll do problem number 1 with you. There's only 3 questions, so this should be a pretty quick homework. I'm gonna help you out and try and find a way to make it quicker for you. Okay, so this says this is analysis of variance. And it's a claim that all the populations here, each sample is drawn from a population and the means are the same. That's your null hypothesis, that each population mean is the same. So in the influential book, Statistical Methods for Research Workers, Statistical Genius Ronald Fisher provides the following example. In an experiment on the accuracy of counting soil bacteria, a soil sample was divided into 4 parallel samples, and from each of these, after dilution, 7 plates were inoculated, which I think means sterilized, but I'm not sure. The number of bacteria colonies on each plate is shown below. Test the claim at 1% significance that the mean number of colonies is the same for the 4 samples. Assume the samples are drawn from normal populations with equal variances, and that's the requirement for the test. Okay, so we're going to need a mean and a standard deviation and a variance from each sample. We'll do that in a second. It says the method for testing the null hypothesis that all means are equal from k different populations is called one-way analysis of variance. Give the null hypothesis is below. Well, it says right here the means are all equal. So that's your null hypothesis in 11.1. The means are all equal. To be honest with you, normally I'd have you write this null hypothesis like this, that mu1, there's 4 means because there's 4 samples here. So mu1 equals mu2 equals mu3 equals mu4. And then the alternative, I'd have you write at least one is different. Ooh, a little messy there. Okay, so at least one mean, I'll say differs. Okay, so that's generally what I'd have you do here. This is good enough, just the means are all equal. Alternative, they're not all equal, which means that at least one is not all equal. So that means at least one is different. Okay, we've got our samples above. You need a mean and a variance from each sample. So I've gone ahead and keyed in this first sample here to the calculator over here. So if I click on data, you'll see the 57.2, there's a 57.2, 37.1, and so on. Okay, so I'm just going to clear out of that and get my statistics. Second data, I want item 2 here for one variable stats. And so the mean's 53.21. It wants how many places? 2 places. So 53.21. All right, so I'll press item 3 here to get my standard deviation. I want to square that so that it's a variance. I get this number. I better approximate that. So we're going to go, and again, it wants 2 places after the decimal. 89.81 is what I'll put in. Like that. Okay, and then I'm not too proud to check that. There we go, looks good. So there's 3 more. Obviously this takes a little time. Feel free to do that on your calculator. You can just keep putting in numbers. Okay, I am going to show you, if you'd like to see it, a quicker way. So I'm going to copy all these. Command C or Control C on a PC. I'm going to open a window and go to sheets.google.com. That's going to give me a spreadsheet here. Blank spreadsheet. Paste. You got to have a Google account, obviously, so for YouTube or whatever. So paste. There are the samples. Get rid of that. And here I want the mean equals average is what you type. You just hit enter and it'll work. Okay, and then for the standard deviation, you can just type equals STDEV for the standard deviation. You're going to have to drag across these now. Click on one and then drag across. Close the parentheses. That'll give the standard deviation. We actually want to square it, so due to the second power, that's with a caret here. The caret is a shifted 6 key on your keyboard to the second. And 53.21 and 89.81. I hope that's what I put in over here. 53.21 and 89.81. Right. All right, but I want to get all of them. So what you can do, once you have one of these in, you can just select them both by clicking and dragging. And then watch what my mouse does when I go to the lower left corner here. It turns into a plus sign. With the plus, click and drag across all 4 samples, and it'll copy the formulas across like that and compute all the means and all the variances. So the second one should be 63.53, I think, and 35.13. What did I say? 65.53 and what? 35.13. Okay, and then the third sample is 63.99 and 40.83. Try it. 40.83, I think is what I said. I'll double check. Yeah. Next one is 60.06 and 28.87. 65.06, 28.87. 65.06, 28.87. I'll double check. Yep. Looks all good. Again, I want to check these, make sure I didn't make a mistake. There's all kinds of places I might have typed wrong. Yeah, see that one. So it says 65.53. Let's double check it. Okay, 63.53. Darn me. It's okay, I get two chances. Okay, I assume you guys got that. Should be okay now. Yeah, everything's good. All right, now we have to do this F statistic. The F statistic requires a sample size N. All the sample sizes up here are 1, 2, 3, 4, 5, 6, 7. So our N is the same for every sample. It's 7. So you put a 7 here. And this one wants the standard deviation of the X bar values squared. So I'll go ahead and read this. In this formula, S X bar squared, called the variance between the samples, is the variance of the sample means. This is the square of the standard deviation of the sample means. When computing this, do not round the standard deviation before squaring it. Then round the result to 4 places after the decimal. Okay, so I go ahead and I'll have to go in and clear the data that I have here. So I'm going to clear that first list, and I'll key in all the sample means, hopefully without making a mistake. 53.21. Then 65.53, then 63.99, and finally 65.06. Yeah. Okay, and then I just need the standard deviation of those. So clear, and then second data, I want one variable stats. And so again, it's the standard deviation of the sample means squared. Here's the standard deviation, but I need to square that without rounding. So I'll just press item 3 to paste the symbol onto the screen and then tell it to square the value. And so 34.34, and it wants 4 places after the decimal. 34.3459 is what I'm going to put in here. Good to me. I don't know. I've still got my fingers crossed. Okay, 34.3459. 34.3459. Okay, so that means I've keyed a bad number in. So now I got to go back to my data. Okay, that's a mistake right there. So I'm going to have to change that to 63.3459. 63.53, like that. Double check the others, 63.99 and 65.06. Okay, these are all good. Okay, and then I can clear out of here. Oh, hang on, let's leave that. So clearing out. All right, so let's try it again. Second, data. I'm doing more variable stats. Okay, and then I want to square that standard deviation, so that's item 3 squared. All right, so 30.5692. All right, 30.5692, fingers crossed. That's good. Now we need the pooled variance. So also in the formula for the test statistic, down in the denominator here, is SP squared. That's the variance within the samples, which is the mean of the sample variances given above. So we just have to average those. So you can just add these up and then divide by 4. You're just averaging them. Okay, so I just realized this should be a 28.86. Just kind of going back, this was rounded incorrectly. That's going to change my computation down here for the pooled variance. And now I need that pooled variance. So I'm just going to key in my variances and average them. So I'll just add them up. So the first one is 89.81 plus the second is 35.13 plus the third, that's 40.83, plus the fourth is 28.86, like that. And again, I'm just averaging those. I'm going to double check them. 28.86, 40.83, 35.13, and 89.81. Those look good. I'm averaging, so I need to divide by 4. And there we go. So here we're going to put in our pooled variance. The average of the variances is 48.6575. Okay, I'm going to check that. Should be good. And then the F test statistics. So you can see the formula I've got over here on my scratch paper here. So the N, again, every sample had a common size of 7, so you can just count 1, 2, 3, 4, 5, 6, 7. There's 7 values in every sample. So down here I'm going to put that N was 7, my common sample size here. Okay, and then my F test statistic is N, which is 7, times the standard deviation of, the variance of the sample means, which is here, 30.5692, over the pooled variance, which is this one here, 48.6575. Like that. So I'm going to do the calculation over here on the calculator. Little fraction here, 7 times 30.5692 over 48.6575. Okay, so just assuming everything was typed in correctly, it should be 4.3978. That's my test statistic. I'm so nervous. And looks like I did it right though, shockingly. Okay, so that's all right. And then it gives the correct value here in case things don't go wrong. Okay, and then it's asking for degrees of freedom. So you have a degree of freedom 1 and a degree of freedom 2. So we already said that n is the common sample size, which that's 7. K is actually the number of samples. So if you go back, you can easily see there's 4 samples here. So K is 4. And then it says degree of freedom 1 is K minus 1. So here, K minus 1 is 4 minus 1. So that's 3 degrees of freedom for df1. That's the degrees of freedom for the numerator. I'll put in a 3 there. df2 is k times n minus 1. All right, so k again was 4. N is 7, so that'll be 7 minus 1. And that's 4 times 6, which is 24. So we'll put that in as 24. And now we can look up a critical value. So again, let's figure out what the alpha was on this one. I don't quite remember anymore. I think it was 0.01, but let's just double check. Right here, 1% significance. We're testing a claim that the means are the same. So alpha is a 0.01. Okay, and then we're going to slide over to the table using, again, df1 is 3, df2 is 24. This is, as it says, I think it's table A5 or A6 probably. Where is it? Table A5. All right, so we're going to slide down to table A5, which I've got down here somewhere. Let me go ahead and highlight that. And it was 3 degrees of freedom in the numerator, 24 in the denominator, which I've got way down here. Okay, and so this will give our critical value, and this tells you what a significant sort of departure from the null hypothesis looks like. It's 4.7181. Okay, so let's go ahead and put that in, 4.7181 as the critical value. I'll check that real quick here, just to make sure. Yeah, that's good. All right, so and then I think I'll go back to the notes here, and let's draw a little picture of what we've done. Okay, so our the F distribution sort of looks a little bit like the chi-square distribution. There's some big differences, but overall it starts at 0 and it's skewed to the right. Okay, your critical value we've determined here to be 4.7181. That's your FCV, critical value. But the test statistic up here we did as 4.3977, which is not quite in the tail. It's here. Okay, so this is our F test statistic, which makes it not significant. Not statistically significant. So that means we're not going to be able to say that we have evidence or data that supports the alternative hypothesis. Okay, so I think we'll go ahead and move on and figure out what our p-value is here. So on this one, it says we're going to move the slider for the F distribution for our test statistic to 2 places after the decimal. So if you go back up here, our test statistic was 4.3977, and so I'm going to make that 4.40 as I slide this over. See if I can get this just right here, right there. Okay, and you can see the area to the right, so 0.013, and that'll be our p-value. These are right-tailed tests always. Okay, and that's a little bit bigger than alpha. So whenever the p-value is bigger than alpha, I'll go ahead and put this in the notes here. So our p-value is 0.01, and then I'll do my obscured 3. This is greater than or equal to 0.01, which is our alpha. Greater means we don't reject the null hypothesis. Okay, and we so we don't support the alternative. H1. Okay, and H1 said that the means are not all the same. So I think we can go on here, say we're failing to reject the null hypothesis and not supporting the alternative. The data, let's see, the data do not support the claim the mean number of bacteria colonies is different, right? We can't say that the means are different. That's the alternative hypothesis, that they're different. So we'll go with that conclusion. And oh goodness, we're 10 out of 10. Everything's good to go here. Okay, so that's it. Best of luck to you.